how we can do the training process. I think this slide is not required since it was well explained ahead. I have a small disclaimer that everything that I say in this presentation is all my own personal view and is not it does not represent the views of my company Quilinia. And I am also not sponsored by any of the companies or technologies I am going to mention here. And the copyrights and ownership belong to those companies. I start with some introduction, more like an application. When we say about image analysis, it's more like we have an input image and we analyze that image and find what is present in the image. Object detection is one such task. So if you look closely into this image, you can see a dog, then there's a bicycle, and there is a truck or a car in the background. So this is one application of image analysis where we can detect what is present in the scene. This is having a quite vast application in scenarios like self-driving cars, and where the car has to detect where is the road, and if there is a person crossing the road, it has to stop, or if there is a car coming in the other direction, it has to do appropriate driving. So object detection is a key application of image analysis. And there is other applications like cell segmentation. This is a more like a biomedical application where you segment the cell. Segmentation means you have an input image and then you separate out the pixels belonging to, say, cell in this case, and then you separate the background from that. So, and if there are many cells, you have to separate out each and every cell, and you can analyze those cells for other applications, like if the cell is moving over time, or it's dividing, or how they are growing over time, and things like that. A medical application. Or you can go for other computer vision applications like a super resolution. So here we have a very low resolution image, like an 8 pixel by 8 pixel image, and you can apply super resolution technique so that increase the resolution, and you can create a higher resolution image. And the ground truth mean it is the actual image. So this original image was downsampled to 8 by 8, and then this image was created. So if you carefully observe, you can see that the ground truth and the created images are very similar. It's not too different from the original image. So these are some of the applications that we can achieve using deep neural networks nowadays. Or you can go for image-to-image translation, like you can convert one object in an image to another, like zebras to horses or horses to zebras, and so on. If you have an image, you can convert that how the image look like in the winter. Or if you have a winter image, you can say how it looked like in the summer, and so on. So those are some interesting application. Or you can go for generating new images, like all the celebrities, or the celebrities like person appearing here. These people does not exist in reality, but they are actually created by a deep neural network. So they are quite photorealistic, and they look like a real celebrities. Or you can go for face transformation, like you give an input image, and then you can say how that person look after, like say 10 years, 20 years, or 30 years. So these are like a oldify type of application. You can also do. Or you can go for style transfer. So it's like you have a top row here and the first column here. So you take features from this first row and combine it with features from this first column image and create a new image. So in this matrix inside, you combine the features from these rows and columns, and you can create a new styles of images. So I think it's quite an interesting application. Or you can also do one more step ahead. It's like you type in like some text. So this is a bird with red and brown color, something like that, and then you can create a bird with that feature. So you don't need to give an image, but only type in how the bird should look like. So this is one type of application. There are many possible applications for these type of deep neural networks. So when actually this deep neural network started, so it all started with this challenge. It is called ImageNet Large Scale Visual Recognition Challenge, or ILSVRC. And it contains like 1,000 different classes of image, and there are 1.2 million images for training. And then if you observe this graph, you can see that in 2011, it was the top 5 error was somewhere near 25. And then 2012, it has jumped like a more than 10% to somewhere around 15%. So something happened at that time. So it was the introduction of something called a deep convolutional neural network. So with the introduction of this deep neural network, the error was reduced extremely. Quite quickly, it was reduced. So people started thinking that, okay, the deep neural network has some kind of potential, so that they got a really good performance in a short period of time. And then afterwards, this competition was won by some sort of convolutional neural network. And you see that somewhere here, it's like a 3% margin. So the 3% is something like a human. This is the error that a normal human can make. So now it has reached a little bit better than the 3% margin, which is like a superhuman capability, you can say. Still, it's a little bit debatable what we call a superhuman capability. So it still, on an average, it's like a slightly better than an average human. So maybe because of this.
Sir, sorry to disturb you, sir.
Yes.
Sir, the slide is not visible in the YouTube streaming, sir. So once again, you
okay.
Close it.
So you didn't hear any of the slides, or? So I see still as it's shared. You still see. I will stop sharing and then I will go again. Can you see the slide moving now?
Yes, sir. Now it's visible, sir.
So should I go full screen?
Okay, sir. Okay, you start, sir.
Okay. I think probably you have missed many of the slides that I have said. So I was saying about this detection here, then the segmentation part here, then super resolution in this one, and then image translation here. So it was more like an application. So we'll go in detail. So I hope you can see the graph now. So this is where this was what I was talking about the different the quick jump in the error reduction. So we'll go in detail. So now we'll see the building blocks, what is behind all these application. So I hope you can see this slide now. So it all starts with this neuron. We know that a real neuron has something called dendrites. where it receives some signal, and then there is a nucleus in the cell, which will process the incoming signal, and then it will pass the processed output to other cells using something called axon. So this is roughly how a neuron look like. And similarly, we have something called artificial neuron. In the artificial neuron, we have input, say x1, x2, x3, and we have weights w1, w2, w3, etc. We multiply the input x with the weight. Each input is multiplied with a weight, and then this value is summed up in a summation device here, and you get a single output from this. And this single output is fed to something called activation function. So activation functions are usually some nonlinear function, and you feed this value to the activation function, and you get an output from that. So this is roughly how an artificial neuron works. So there are different type of activation functions. Some like these are the three popular ones used nowadays. So one is called a tanh function, which is the value varies from -1 to +1, or it could be sigmoid function where the value varies from 0 to 1, or it could be ReLU function, which is like it's called a rectified linear unit. So in ReLU activation function, all the values less than 0 is dropped, and all the values 0 or positive values are passed to this activation function. So that type of function is called a ReLU activation function. This is the most popular one used in the neural networks nowadays. And when we say about deep neural network, what is actually a deep neural network? So for a general neural network, it has got an input layer, like here, where we feed the input to the network using this input layer, and there is an output layer where we get the output from the network. And between this input layer and output layer, there are several layers, like they are called hidden layers. All these layers are hidden layers because we cannot directly access them outside. If a neural network has got many hidden layers, like many layers in between the input layer and output layer, then we call it as a deep neural network. So how deep it can go is it's still not very clear. So maybe it can be like a 10 or 100 or 1,000 layers. There can be like that. Or if it's like a 1 or 2 layers, then it's more like a shallow network. So whenever you hear the term deep neural network, you mean like it has got many hidden layers. So coming to the types of deep neural networks, these are the three popular type of deep neural network. One is called a convolutional neural network, another one is called a recurrent neural network, and another one is called autoencoders. These are just a rough classification. We can mix and match any of these different types and create your own new model type of novel neural networks. So we'll see a convolutional neural network in detail in this session. So convolutional neural network. So before we go to the convolutional neural network, we just go back to the old network type. So this type of network is called a fully connected network. So where we can see that this node is connected to every node before it, like this. So every node is connected to every other node before it. So similarly here also. So you can see that there are so many connections going into this single node. So when coming to this convolutional neural network, this node is connected only to 3 nodes here. So that means it is not connected to every node, like in the fully connected layer. So they only have got a local connection. So this connection is local to this node, and the spatial relationship is preserved. What that means is like if there is something happening at the top of this signal, it will be reflected here, and something happening and this part is not reflected here. So anything that is happening here is reflected only in this part. So this the features at the top part of the signal is present in the top part of this output. Similarly, the features at the bottom is present in the bottom. So spatial relationship is preserved in this type of network. And you can see that this green values these are the weights. So these weights are shared between all these input values. So we have a parameter sharing happening here. The same parameter is used in all these different input signal. And this is widely used in image analysis because of these properties. This is a one-dimensional case. So similarly, the case with the two-dimensional case where we have images which are two-dimensional in most cases. So this is like a two-dimensional convolution. We have the row and columns, and these are the weights distributed here in this row and column format. And this filter value move around the image, and then you get the value at the next layer, like this. This is like a
sir, again, sorry to disturb you, sir. Sir, now the slide is not changing in the YouTube streaming, sir. In YouTube streaming, around the image, and then you get the slide is activation function alone.
Okay.
Sorry to disturb you, sir. Sir, now the slide is not changing in the YouTube streaming, sir. In YouTube streaming, yes, sir. Now it is activation function alone.
So is the slide visible now?
Yes, sir.
I will not go into the full screen mode then.
Okay, sir.
So if you have any questions, then we can take that at the end if something is not clear.
Okay, sir. Okay.
So, this is like the two-dimensional case where we have images. So we have this row and column of filters, and then it moves over the image, and you get the output at the second layer. And in the neural network, we have a 3D convolution where you have like a 2D, and then there is a depth layer. So you have several 2D images stacked together. So in this case, you have like a row, column, and a depth-wise dimension for the filter. And this green filter, when it moves through this input layer, you get one output at the next layer. At this red dot. So you can see that this is moving over here. And similarly, this yellow filter, when it moves through the image or the features, you get like a one output at the layer that is behind the red one here. So it's the blue one. So this is how the convolution happen in a neural network. And when you perform a convolution on an input layer and you get an output, like a value at the output layer, and these single two-dimensional images are called feature maps. So you have several feature maps. You apply one convolution and you get one feature map, and then another filter value, then you get another feature map. So it goes on like that. So these filter coefficients, these green and the yellow values, are learned from the data. So that's when we train the neural network. And this can be implemented as a fast matrix multiplication in modern CPUs and GPUs. And nowadays, efficient GPU implementation for matrix multiplications are available, so can do things faster. And these are usually implemented as tensor multiplication or addition. The tensors are like more than three-dimensional matrices. And you can go for hierarchical feature extraction. What that means is you can create, you can apply a convolution using this filter, and then you get the output at the next layer. And similarly, you can create mini layers like that, and then you can repeat the process again. So this one become the next layer, and you can apply other filter on top of this newly created feature maps, and you can extract more features hierarchically. So we can continue this process again. So we might think that these convolutional neural networks are quite a new idea, but you can see that as early as 1989, it was used for real world application. So this is one such type of convolutional neural network where it has got several convolutions and other type of layers. And this is the network that I mentioned during the slide that I mentioned, that when the top 5 error was reduced in 2012, and this was the neural network that was used for that particular application for ILS VRC challenge. So here you can see that there are several convolution layers, and here they operate on the input image and then get the output. So you can say these are the first deep convolutional neural network. And later we have seen that there are several deeper and more complex type of convolutional neural network happened. And this is one example for that. These blue boxes here are convolution layer. So when you say how deep a neural network is, we count the number of learnable layers, like these convolution layers in this one. And this is a zoom in location of one part of this here, one part of that big deep neural network. So here you can see that you can design your network in different ways. You can have like a several parallel convolution with different sized filters, like a 1 by 1 or 3 by 3 or 5 by 5. You can have your own type of neural network and connect in any way you decide. So this is just an example of that. These type of networks are used for classification. That means you give an input image here, and you get a single value at the end, where this value, the output value, say which class the image belongs to. Or in this case, this is called a U-net because it has got the shape of a U, like this. So this is more like a segmentation network, and it is a popular one used in biomedical image analysis. So you give an input image here, and it will pass through all the different convolution layers, like these blue boxes here, and then it will upsample the image, and you get an image at the end. So you feed an input image, and you get an output image from this end, and you get an output segmentation map. So this is like a segmentation neural network. So it depends on how you design the network and how it behaves. Another type of neural network is called a recurrent neural network, which is in this network, it forms a direct cycle. So when you connect one layer to another layer, it's not like a direct connection. It forms some sort of a loop. So, and you can decide how many times it should loop and things like that. And creates an internal memory. And this type of recurrent neural networks are used for processing speech or text or video and things like that. And long short-term memory, LSTM, is commonly used type of layer in that particular type of recurrent neural network. And another type of neural network is called autoencoder. So it is used for unsupervised feature. It basically means like you give an input here, and it will downsample, sort of reduce the dimensionality of the input and create a code at the middle here, and then recreate this original image or original input from this code value. So it's like encoding here and then the decoding step in here. You can combine several of these layers, this type of encoding, decoding structure, and create a deeper neural network. In its original form, it is not used nowadays because of the difficulty in training them and other problems. but nowadays these type of networks are combined with the previous types and then created a new type of neural network. This is one of the such type of applications. It's not image analysis, but more like I thought it's an interesting topic as well. So this is like a recent paper came and using this autoencoder LSTM type of neural network, where they convert from C++ to Python language. You write the code in C++ and you get you can convert that into Python. Or you write in Python language and you can convert that to C++ language. Or you can also convert to Java or any other different type of programming language. So this is one of an interesting application using neural network. Different components of neural network. So we'll see that in detail. So a deep neural network contains several of the mathematical components. So they are like roughly there. I mean, there are more than this, but these are like the rough estimate of what it is actually. So it uses linear algebra, optimization, and calculus, and information theory, then parallel programming to make everything run faster. So in the linear algebra, it contains the matrix operation. So we have seen that there are matrices. So it involves matrix operations, matrix multiplication, addition, tensor operations, if there is more than three-dimensional matrices. And we already have efficient routines like BLAS, open BLAS, and things like that. So we can solve this linear algebra using this BLAS, which is already existing before introduction of deep neural network. So we can just use them. Optimization. So optimization means finding the minima of a function so that we get the optimal performance of any system. So in this case, we have a loss function, which is part of optimization. Then we have the optimization space where we minimize the function parameter. And we find the parameters, which are like the weights in the neural network. It could be millions of parameters like that. And we use a technique called stochastic gradient descent or its variant to do this optimization. And then there are several hyperparameters, which are like parameters outside the neural network. We have to tune these hyperparameters to get a best performance. And we have a problem of overfitting to the data, or we are trapping in the local minima or trapping in the saddle points. Saddle points means they are minima in one direction and maxima in the orthogonal direction if you move in the optimization space. And there is also regularization, which is used to minimize the overfitting. So we don't want the neural network that we designed to be overfitted to the training data. So use regularization techniques for that. And then calculus. So in calculus, we use a chain rule of differentiation. So we find the derivatives, and we'll see how it is in the later slides. And we apply matrix calculus, and which is like a large matrices of derivatives we use. And this is the base of backpropagation algorithm. We'll see that later. Coming to information theory, we have the loss functions. There are several different types of loss function to calculate. And then there is something called KL divergence, which is used to find the similarity between two different distributions. So when we train a deep neural network, we try to match the distribution that we create using the deep network match with the data, so that the divergence is less. Then parallel programming to run everything run much faster. Training or testing process to run faster, we use parallel programming. And we use GPUs for that in normal cases. So we have CUDA, OpenCL, OpenMP, ROCm. These are different tools for doing the parallel programming. And there are several companies coming up with the different tools to do this. And we also have a tensor processing unit, so where we can use this tensor processing unit to run everything much faster. So now we'll see how the training actually happens. So how does the neural network learn? So we have seen that there are different parts of the network and how they actually learn. So these neural networks, they transform input to output. So we give an input to the network, and the neural network do some operation on that, and we get the output. And this is called a forward pass, where we like the forward pass, this process of giving input, processing in the neural network, and getting the output is called a forward pass. And then the neural network learns from its mistakes. So we have to quantify this mistake. How large is the mistake, or how small is the mistake? We have to quantify them. We use a loss function to find the how large or how small the mistake is. And then we want to find the effect of each parameter in making this mistake. So we want to see which parameter is contributing more to this loss. Which, if we change that parameter, whether we get lesser loss next time or something like that. So for that, we use something called a backward pass or backpropagation. It's also another name. And then we have to increase or decrease the parameter value so that it will make less mistake next time. So for that, we use something called stochastic gradient descent, which is the optimization step. And then what we have to do is we have to do this all of this process several times. So then we call it as iteration. So that's how a neural network learn. So we'll see what is a forward pass. This is an illustration of how the forward pass actually happens. So we have an input, and during the forward pass, it passes through the next layer, and it goes to the subsequent layers, and it reaches the loss function. And this loss function calculates the loss value using the input or the output from this neural network and the label. So a label is the ground truth, or we decide how the input should be. So this is like the input is the neural network map the input to the label. So this is like a already created image or class or something like that. So we want this input to be classified as this type, and this loss function that we have used, it will take this label and the output from the network and get the loss function. So then we calculate the gradient of this loss, and then we calculate the gradient for all these different layers. So then we calculate this layer for this layer and this layer until we reach the first layer. So forward pass is, it starts from the input to the output, and then the backward pass is from the output to the input. Once we have calculated all the gradient, we have to update the parameter. So we calculate the gradient and then update the parameter one shot for every layer. And then we repeat the process again. So this is how the forward and backward pass and the update happens. Then the parts of actual training. In actual training, we have this the training process. Then there's a loss function, then the forward pass, backward pass or backpropagation, and then gradient descent optimization. So these are different parts we use for training. So we'll see in detail. So what is actually how we can do the actual training process? So for training, we need data, or we have to prepare our data set ahead of time. And then we divide the data. This is an important part. So we should never forget this data partitioning step. So we take the training data, we take the data set and divide it into training set, then a validation set and a test set. So training set is the actual training data that we train the network on. And this validation set is a set that we validate our network. That means we measure the performance of our trained neural network using the validation set. And when we are satisfied with the validation accuracy, then we need to go for the testing. So this process, the testing is done only once. If we do testing more than once, then this testing set becomes the validation set. So we should always remember to keep this data in these three different partitions. So what actually happens if we don't do this is we get when we train on the training set and test on the same set, then we might get a very good performance. But if we test on a new test set, which is not used for training, then we might get a very poor performance. So we say that the network is not generalized in that case. So it's important to keep the training, validation, and test set separate. Then we have to pre-process the data like a zero mean unit standard deviation, or normalizing the size of the image. Say like usually the images are of 224 by 224, 256 by 256 size, and things like that. And we have to design our neural network architecture. So we have to design the network ahead of time. Then we need some hardware to train, like a GPU for training. And we go for some weight initialization. We have to initialize the weight. We cannot initialize with a zero weight. It has to be non-zero values. It has to be non-symmetric. If they are symmetric, then different parts of the network learn same features and they become kind of redundant. So we want a non-redundant network. So we have to. So then it learns more features. And we have several distributions like a Xavier, Chi-mean, etc. for this weight initialization. Function. There are several different types of loss function like SVM loss, hinge loss, softmax cross entropy loss, or discriminator loss. So these are different types of loss that it depends on the task that we have in our hand. So based on the task, we change or use the appropriate loss function. For classification and segmentation task, we normally use softmax cross entropy loss. And then backward pass. In the backward pass, we follow the chain rule of differentiation, and we have to find the analytical gradient of each and every component. So we know the equation for the forward pass, then we have to calculate the gradient or derivative of that function, and find the derivative of activation functions, which type of activation function we are using. We have to find the derivative for that. And then this is the chain rule, like the total gradient is the product of the gradient at that node multiplied with the gradient coming to that node, which means the partial gradient, the derivative at that point multiplied with the partial derivative that's coming to that node. If it's connected to multiple nodes, then we have to add the gradients. For ReLU activation, rectified linear activation that we have seen earlier, we pass the gradient only to the positive output. So ReLU means we have seen that it only passes the positive values to the output. So we only have to pass the gradient to the positive values only, not the negative values, which are all we have blocked. So this is a toy example of how the backward pass or backpropagation algorithm works. So assume that we have a network like this, and it has got input x, y, and z, and there is the function like addition here and multiplication here, and you can see that f equals q multiplied with z. F is q multiplied with z here, and q is x plus y. Q is x plus y here, and derivative of f with respect to q is z. So derivative f with respect to q is z, which is quite like an elementary calculus. Similarly, derivative f with respect to z is q. And for this equation, we can see that derivative q with respect to x is 1 and q with respect to y is 1. This one, with respect to these two. And this is the chain rule. If we have to find the derivative of f with respect to x, we have to find the derivative of the in-between value and then multiply it. So if you see the input, here x is -2, y is 5, and then this q become 3, and then it's multiplied with the -4, you get a -12 here. So all the green values are the forward pass, and then you get you have to find the backward pass. So for the backward pass, you have to start with the 1. Why this one? Because it's the derivative of f with respect to f itself, so it becomes 1 here, and then we go back in this direction. And then we can substitute these values in this one. Derivative f with respect to x is derivative f with respect to x here is derivative f with respect to q multiplied q with respect to x. So which is f with respect derivative f with respect to derivative with respect to q is z that we have already calculated here. So the original value is -4. So that -4 become the gradient here. So it's the red in here. And similarly, then the next gradient is derivative of q with respect to x is 1, which already we have calculated here. So this -4 is multiplied with the 1 here, and you get the gradient here. So that's how the gradient is calculated. Similarly, this 3 comes here in the opposite other way. Also, so hope this make a little bit more sense for this backward pass or back propagation algorithm. So we have a forward pass, then we calculate the gradient in the backward direction, and you get the values. So we have seen earlier that once we have the gradient calculated, we have to update the parameter. So we use an algorithm called gradient descent for that. So assume we have an objective function, we name it as j of theta, where theta is the parameter that we have in the neural network. So which is actually the weights in the neural network. It's an element of, let's say this is the RT. So where D is the number of parameters. D could be like say 100,000 or a million, it can be. Then we have to find the gradient of the objective function. So that's how we have seen in the backward pass or back propagation algorithm. We have to find the gradient of that. And then we have to update it in the opposite direction of the function gradient. So what happens if we update in the same direction of gradient? So we get more gradient next time. So that's not what we want. So we want a less gradient next time. So we update in the opposite direction. So it's just like just put a minus sign in front. And then we have a learning rate, eta. So this learning rate decide how much of the gradient we need to update. So which is like a, say it could be a constant or it can be like a weighting value. So we don't want the parameters to be updated quite large. So we want like a small value. So we multiply the derivative with the small value and update the theta. So this is the old theta and this is the gradient, and multiply with the small value, and the new value is this updated value. And for gradient descent, we use several type of ways. We call one type is called a patch gradient descent. So patch gradient descent is like we use the full data set per update. So we have seen like a forward pass, backward pass, and then update of parameter. So for in the patch gradient descent, to update once the parameter values, we have to go through the entire data set. Say we have 1,000 image, then we have to find the gradient of when after passing these 1,000 images, and then update the parameter once. So that's a patch gradient descent. And then the next type is called a stochastic gradient descent. So in the stochastic gradient descent, we pass one image, find the gradient, and update the parameter, and then pass the second image, then do this process again and again. So these two are like the extreme. So one is like a pass the whole data set, and the other one is like a one image at a time. And these are two extreme cases. And then the last one, mini batch gradient descent, is one in between these two extremes. So here we pass a subset of the image. So assume that we have 1,000 images, and then we pass, say, 10 images at a time. And after passing 10 images, we update the parameter. So that's a mini batch gradient descent. This is the most popular one used nowadays because it's more memory efficient and we can train faster. So this is an illustration of how the stochastic gradient descent works. So probably during the beginning of training, the loss is somewhere here, and it over time with the iteration it will change all this way, and it will go and finally reach the minima in here. So this is roughly how the training process happens. And we have seen that there is a parameter called learning rate. What is the effect of learning rate? So if we choose a very high learning rate, over time this loss function decreases and then increases. So we have seen something called epoch here. So I will say what is an epoch. So epoch means if we analyze the whole data set of say 1,000 images, then after we analyze 1,000 images in our data set, it's called one epoch. So it's the number of time we analyze the entire data set. So we have to keep in mind the difference between iteration and epoch. So iteration is the number of updates that we make to the parameter, and epoch is the number of time we pass through the whole data set. What happens if we have a low learning rate? It's like then over the increasing after the several epochs, the loss function decreases quite slowly over time. And if we have a high learning rate, it will decreases quite steeply and then almost stays there. And if you have a very good learning rate, it will decreases quite smoothly over time with the epoch. So it's important to take an appropriate learning rate. It's a little bit difficult to find, but it's a trial and error thing. And variants of gradient descent. So we can add some more extra terms to the gradient descent. We can apply momentum. Like if we get a higher gradient, and then we can, using the momentum, we move in that direction a little bit more. So we can get a better loss quite early. So we can decrease the loss earlier, or we can use nested of accelerated gradient. It's like a approximately predict the next value of this gradient, and then you go directly to that value. And if it's error, then it will make a different like a correction. So that's how roughly the nested of accelerated gradient works. Or we can go for adaptive methods like AdaGrad, AdaDelta, RMSProp, or Atom. So these are different adaptive methods. We can they work independently of each other, and then you can get a better performance quite faster using these techniques. Regularization. The regularization is a way to minimize the overfitting. So we use data augmentations. That means we flip or rotate the image to get more data. Or you can use a dropout where you drop the connection between layers, and every time you go for a forward pass. Or you can go for batch normalization. So the output from the output of feature maps are like a normalized. Maybe it could be a zero mean unit standard deviation type of normalization. Or it could be a batch-wise learning, like a mini batch learning, mini batch gradient descent type of learning. That's also a regularization step. Or you can use local response normalization, is another type of regularization technique. Or you can go for L1, L2 regularization of weights. So L1 means you give priority to higher priority to some weights than other weights, or you can give equal priority to different weights using L2 regularization. And there are so many other hyperparameters you have to tune for getting a better performance, like the learning rate that we have seen, or learning rate decay. That means how much the learning rate should be reduced over time. Whether you want to use momentum, network depth, that means how many layers that you have, or network width, that means the number of filters per layer that you have, and or the mini batch size, whether it should be 10 images per batch, or it's like 100 images or 60 images. So that's also a hyperparameter that you have to decide. And then we go for a little bit of implementation. So how can we implement these deep neural network? There are several software tools like PyTorch, TensorFlow, MXNet, ML.NET, or DL4G. So these are all open source software that we can use. The first two are Python based. You can use any of these modern deep neural network tools to train your own neural network. And there are other software tools like TensorRT, OpenVINO, or ONNX. So this using TensorRT, you can run it much faster on a GPU, or you can use OpenVINO from Intel to run on their hardware as well. Or you can use ONNX to. This is used to convert from one software tool to another software tool. And we can use hardware accelerator from different companies. They have different type of hardware accelerators. There's NVIDIA LA from NVIDIA, then Neural Compute Stick, or Google Edge TPU, or you can program your own FPGA as a hardware accelerator for your task. We just give a quick look at how difficult is it to program a neural network. So we know that we need the data for our training. So we get data from this step. So we get input as well as the label. The label is the ground truth and how the output should look like. And in this step, we just zero out the gradient. So this is like a start of the optimization. And then net is the neural network that you have designed, and you take the input and pass it to this net. That's a neural network, and you get the output from here. So you get the output, and next step is you use this output and put it to the loss function. So loss function is also called as criterion here, and you pass it to this criterion, this output from the neural network, and the label that you get from this data, and you get you calculate the loss. So this is the loss function, this is the forward pass, and the next step is the backward pass or back propagation. So you type this command, loss.backward, and you get the backward pass. And once this step, you get all the gradients in place. And then after finding all the gradient, you step one step, or update the parameter. That is done using optimizer.step. So you can see that only 4 lines of code is used to program or train your neural network. And then we should not forget the last step, that is this for loop. So we had to repeat this process several times. So that's the for loop doing here, and it's passing through the whole data set. So you can see that it's not necessary to calculate all the forward or backward pass by hand. So any of this modern deep neural network tool can be used to train your own neural network very quickly. It's not difficult. It's very easy these days. And this is an extra thing. I hope we have some more minutes for this. So this is like a popular one used nowadays, which is called a generative adversarial network. We have seen that we can use neural network as a function approximator. That means we can give any input to the network and get any output. So using that convention, we can say that we pass a noise to the generator network. This is a neural network, and you get some data. So it could be fake data. And you can create another network that's more like a classifier. Here we call it as discriminator, and it will get a fake data and a real data, and it will say whether it's a fake data or a real data. And we can combine these two network in a smart way to get this type of a network connection, and we call it a generative adversarial network. So these two networks are trained simultaneously, and they are optimized at the same time. And once some sort of equilibrium is reached, you can this generator network can create any type of data that we want. So this is the network that was used for generating the faces or converting from one type of like a summer image to a winter image, or winter image to summer image, and things like that. So those type of nice applications were done using this type of a configuration. I think that's all I have for you today. And I think we can take some questions if we have time.
Thank you, sir, for such an informative session. Participants, if you have any queries, you can ask. Kindly put it in the query chat box.
I can share the slides with the organizers so that if you have some questions, you can contact me later also.
Okay, sir. Thank you, sir. Now I invite Mr. P. Kannan, sir, Assistant Professor of ECE Department, to deliver vote of thanks.
Good evening, all of you. It is a great honor to propose a vote of thanks on this special occasion. First of all, I thank Lord Almighty for giving this opportunity to conduct this webinar. At the outset, I thank the resource person, Dr. Sajid, for having presented the webinar on image analysis using deep neural networks. Sir, on behalf of ECE department, I thank you for your wonderful webinar, sir. Next, I thank the management for their guidance and motivation to organize webinars during this lockdown to make our students and other participants enrich their knowledge in relevant fields. Next, my sincere thanks to Dr. K. Jayakumar, General Manager Development, and Dr. V. Velmurugan, Principal, and Dr. Ella Priya, Professor Academic, for their endless support. Thank you, ma'am and sir. Further, I take this opportunity to thank Professor J. Friska, head of the department, for your valuable advice and direction towards making this webinar a grand success. Thank you, ma'am. Next, I thank the coordinator of this event and all the faculty members of ECE department. Finally, my sincere gratitude to all the participants for your active participation. Thank you, one and all. Thank you.
Thank you, sir. For the kind attention of the participants, feedback link will be posted in the description box as well as in the chat box. Once again, thank you all for joining with us.